Hello everyone, this is the Mining Geologist and I'm back again with another very exciting and very informative tutorial. Today we're going to be looking at something a little bit different and because we're not covering a software, that's the first thing. The second thing, this video is going to be a little bit longer than the usual videos that you guys used to see in this channel. So stick around, be patient, because I guarantee you're gonna learn a couple of things today. So this video also was based on a poll that I ran a couple of days ago here on YouTube and on LinkedIn also. So if you're not following me on LinkedIn, make sure to follow me on LinkedIn. The links is gonna be all the different links related to me are gonna be in the description below. So make sure to check them out. And I've asked you guys whether you are interested to see Python related application in geoscience and see me cover a few things in Python. So that's what it is all about. And a lot of you said yes, they were interested, and here we go. So before we dive into programming, I wanted to go through a few slides in which I'll try to explain what is going to happen and how the ordinary Kriging is going to estimate these unknown points based on some known points. And of course there will be some assumptions. So I think that you're familiar with the basics of geostatistics, and you know that we cannot jump into Kriging without doing a variogram model and without defining the type of the model, whether it is like a spherical one or exponential or whatever. So in this tutorial, we are going to assume that we have a spherical model, and we are going to assume that we've done the modeling and we have already the nugget, the cell, the range, and so on. And all we have to do is we are going to apply that semivariance equation to whatever lag distance or distance that we have to get the semivariance value for that specific one. So these are the assumptions that we're going to use, and without further ado, let's get started. So as you can see here, we have a bunch of points. We have 1, 2, 3, 4 known points, which are P1, P2, P3, and P4. And for these points, we know the X and Y coordinates, and we also know the value, which is called V in here. And this is a variable. It could be grade, for example. Let's assume that it is a grade. And as you can see that we have a point P5 that it is unknown, and we have the X and Y coordinate for that point, but we don't know the grade in there. So usually Kriging, what it is going to do, how it is going to estimate that point, it's going to assign some weights to the grade values in the known points, and then based on these it's going to calculate the value in the P5. Of course the weights are going to depend on some factors like the distance, for example, and sometimes the distance it's not it doesn't really reflect the weights. For example, if we have a continuity in this direction and not in this direction, so the weight in P1 could be higher than P3, for example, even though that P3 is closer to P5. But we're not going to do these kind of directional stuff. It's a little bit advanced to cover that, and we might do that in a different tutorial. So we're going to assume that it's purely based on the distance, and we're going to say that that's what we have now. So let's go and see the mathematical operations that we need to cover in order to estimate that P5 using ordinary Kriging, because there is simple Kriging, universal Kriging, and so on, and each one of them have something different. So for example, in the simple Kriging, it's going to assume that we know the mean, the global mean, and we're going to use that and also some residuals in order to calculate or estimate the P5. But in the ordinary Kriging, the assumption is that we don't know the mean, and we're not going to use that, but instead we are going to assume that the sum of the weights is equal to 1. Okay, so let's keep that in our minds, and let's move to the next thing. So this is exactly what we are going to do. So basically we have, the first thing is that we need to calculate the different distances. So we have all the combination of distances. So for example, we have the point, so let me go to the first one. So it's going to be the distance between point 1 and point 4, point 1 with point 3, and point 1 between point 2, and so on. To calculate all the different distances. Also, we're going to calculate with the P5, but we're going to set that aside. And then we're going to do this with all the different points. Then P2 with P1, calculate the distance. P2 with P3, calculate the distance, and so on. And we're going to create a matrix with that. So we have the distance of point 1 and itself. So this is going to be basically 0. The distance between point 1 and point 2. The distance between point 1 and point 3, and so on. You can see that, for example, so the point 2 and itself is going to be 0, so we're going to have a bunch of zeros on the diagonal in here. So there's a mistake that I've done here. So this one should be 0, because on the diagonal we're going to have a bunch of zeros, not 1 there. So let's get back. So as you can see, so forget about the different ones in here. We'll see what is why we add these there. And then what we're going to do is we are going to have the varigram model. We have the semivariance equation, and we have the nugget, the cell, and so on. And using these, we are going to calculate the semivariance for that lag distance, which is the 0 in here. And then going to calculate it for this distance here, for this distance here, and so on, until we have all of these, semivariances. And also, what we have here, we've added a bunch of ones to this one. Why do we do that? Because we said that the sum of the weights, which are, these are the weights, sorry for that, let's just cover one thing at a time. So basically, if we multiply this one, we're going to get the semivariances of in that unknown point. So for example, we'll see we get the semivariance between the distance of point 1 and that unknown point, which is P5 in our case, and we're going to get that for all the different points. And why do we add these different ones in here? That's, if you go back to the matrices, the dot product and the multiplication and so on, you'll notice that in order to get the sum of the weights to be 1, we need to add these kind of things. So we're not going to cover how is that done, but that's the purpose of this. So it's a pure mathematic in here. In order to get 1 in here, we need to add all of these ones and this 0 in here to get 1 in here. And this is the assumption that we have in the ordinary Kriging, is that the sum of weights needs to be 1. Okay, so that's why we add these things in here. So now in mathematics, so if you have, for example, 10 multiplied by 2, we're going to get 20 in here. So how do we get the 2 in here, which is the weights? It's easy as dividing the 20 by 10, which means we divide B by E to get the E. Okay, so how do we do that if we have matrices? We don't have, we cannot do matrix division, but we have something else, which is we can do matrix inversion. So B divided by E could be E minus 1, which is the inverse, the inverted, E matrix multiplied by B to get the weights E. So our problem now is to get the weights, and that's how to get it. Then what we can do is we multiply the weight of the point 1 with the value of point 1 plus the weight of the point 2 with the value of point 2, and so on, to get the estimated value of that 0.5. So this is all about ordinary Kriging. It's not really that complicated, not really that hard, but how to do that programmatically. So there will be a few steps involved, so let's cover them now step by step. So the first thing is using this distance. This is how to calculate the distance between 2 points. It's really straightforward, and you can see that we are assuming that this is just in 2D. We're not doing this in 3D. So all you need now is x and y coordinates for these two different points. But in 3D, you will need also the elevation, and this is going to complicate things a little bit, so we might do that in a future video, or maybe like a second part of this one, and try to update the script that we're going to create. So we're going to create what we call a distance matrix. So we have all the points here, P1, P2, P3, and P4, and we have them also in here. So the distance between P1 and P1, it's going to be 0. And then we calculate the distance between P1, the distance between P1 and P2, the distance between P1, and so on. And also, on the right side here alone, we are going to calculate the distance between P1 and P5, P2 and P5, P3 and P5, and so on. So keep that in your mind. Then, if you remember, we said that we are going to calculate the semivariance of that lag distance in here. So in our case, this is going to be 0. So we're going to apply this equation here. And like I've mentioned, that this is going to be, in our case, we're going to assume that the model is a spherical model, the variogram. And if it's a different one, exponential, for example, this equation is going to change. So keep that in your mind. And for this one, we'll need, when we model the variogram, we're going to get the nugget, the cell, the range, and h is going to be the lag distance, which is these distances that we're calculating. And basically, we're going to replace these with the values that we have, and this is going to give us a semivariance value in here. And we're going to, calculate these for all of the different distances that we've calculated. Okay. The next step is to cover that part in which we said that in the ordinary Kriging, the sum of the weights needs to be 1. So to do that in the matrices, in matrix operations, we need to add a column of 1 in here, and a line, a row of 1 here, and the sum is going to be 1 in the P5. So that's how we cover the part of the sum of weights needs to be 1, in matrices. So that's the second step that we need to do, is to add a bunch of 1s and a 0, of course, since on the diagonal here we have all of, we have zeros. Okay, then the second step is what we need to do is basically we need to, for this matrix that we've created, we need to do the inverse of that matrix. Okay, so you can go and Google that, and you will find tutorials. Basically, if it's like a matrix with the shape of 2 by 2, it's not going to be really hard to do that manually with your hand. But imagine if we have a grid of, let's say, 100 by 100. Trust me, calculating that manually is going to take you a lot of time, and it's really a tedious process. So we need to do this, using computers, and that's what computers are made for. So the next step is we have this one, which is a minus 1, which is the inverse of that matrix, and we're going to multiply this by what we said that this is going to be b, and what are we going to get is the weights. So now we have the weight 1, 2, 3, 4, and 5. That in our case, this is going to be the weight for the point 1. This is going to be for the point 2, 3, and 4, and we don't need this one. So, and how do we calculate the estimated value at the point 5? It's basically going to be the weight of that point 1 multiplied by the grade of the point 1, the weight number 2 multiplied by of the point number 2 multiplied by the grade on the point 2, or whatever variable that you're working with, and so on. And the sum of this is going to give us the grade at that point 5. Now this is the basics of ordinary Kriging. I'm sure that maybe I've missed something, and I don't know. So this is, I've tried to simplify this and make it as simple as possible, so later on when we're doing this in Python, you know exactly why we're doing this. So when I say we're going to create a function that's going to calculate the distance between 2 points, you know that I'm doing that in order to create this distance matrix. When I'm creating a bunch of arrays to add these bunch of ones to an existing matrix, we're doing this to cover the part where the sum of weights needs to be 1. And when I'm creating a semivariance equation, that we need a variable that have the C1, the C0, the nugget, the cell, the range, and so on. And so this is just to give you an idea about the different things that we might need. And we have now the steps that we need to cover in order to get that point estimated. So now let's go and jump into Python and see how we can do this in Python. Okay, now we're in the Python interpreter, and we are going to go through the code. So instead of going and writing this again, and this is going to take way longer than I really expect, so I decided to go through the code and try to explain it step by step and what each one of these lines is doing. And of course, if you guys think that I've missed something or there's something not clear, you can still go and comment in the bottom, and I'll do my best to explain things for you. And to be honest with you, I'm gonna assume that you guys know the basics of Python, and I can't go and explain what is a variable, what is a for loop, and what is an index of a list, and so on. So I'm gonna assume that you guys know these kind of things, and if you don't know, feel free to pause the video and go and check out. There's plenty of tutorials on YouTube and over the internet that cover the basics of Python. Okay. So the first thing that we need to do is we need to import all the different libraries that we're going to use. So basically, NumPy is, we're importing NumPy is it's a numeric Python. This library is used to manipulate matrices and to do all things related to vectors like the dot products and matrix multiplication and all sort of things that you can do with matrices, you can do with NumPy. Pandas is basically a library. You can think of this as if you have an Excel sheet, but you don't have a limit in the number of rows. So if you guys know that Excel have like a limit of, I believe, 1,400,000 and so in number of rows that you can use. But with Pandas, you have your computer is only the limit, so you can have maybe 10 million rows in a Pandas data frame, and you can manipulate that the same way you do in Excel. So maybe you can add the first column with the second column to the third column, or maybe you can do division, or maybe you can filter out some values. Let's say that you have some grade values and you want to filter everything that is above, let's say 5% or whatever. You can do that with Pandas, and this is what it is basically about. These two libraries are really important, and they're used a lot in machine learning and stuff like that, and also in geoscience we use them a lot in our scripts and algorithms. Okay, then we have the library math. Basically for this one, math, we need only the sqrt function to calculate the distances. Other than that, currently we don't need that, but maybe if you have a script in which you do a lot of trigonometry. If you've been following me on LinkedIn, and I posted that dynamic bit designer, well, for that, the math library, you need that a lot because we're doing a lot of sin, cos, and so on. So you will use that math library a lot. So these are the different libraries that we're going to use. Of course, if you want to do some visualization, if you want to create like a contour map with the values that you're going to interpolate and so on, you can import matplotlib, for example, or plotly, or you can do any other library that is used for visualization. You can do that, but we're gonna consider this as a bonus. It really, if you want to do that, you can do it. You can or let me know in the comments below if you want to see this in different visualization tools, and we can maybe make a map for this one. And I already did that, but let's make this a simple one. Now, if you guys recall, in the first part of this video, I told you that we're going to have some assumptions. We're going to say that we've already modeled the variogram, and it's a spherical variogram, and we have these values: the nugget, the cell, and the range. The range is I wrote it here without an E because range in Python is already a built-in function, so we cannot use that one. So let's call this range, or maybe you can call this range here, or I decided to use that just range without an E. So these are the values that we're going to use, but you can change these later on and you see the effect, for example, of the nugget. If we set it to 0, how is that going to affect the interpolation? If we set the cell to, I don't know, like 5, you see how is that going to affect the interpolation? And later on, if you want to make this a little bit advanced, we can make some sliders, so we can change these values and see the map changes and so on. These are a lot of ideas that you can play around if you get to create a simple script like this one. So this maybe, if you think about it and if you understand the math behind it, it's not going to take you like more than an hour to create such a script. So it's not really that hard to do. And let's go and dive into this one and try to explain what each one of these functions is doing. Of course, again, I'm not a programmer, I'm not a software developer or anything like that. Everything is self-taught, so I might do some stupid things here and there, and I will find these, programming gurus in the comments below telling me that's not the right way to do this, or there's a way, another simpler way to do this. That's not my main goal here. My main goal is that, I show you guys how easy it is to create these kind of things, and we always learn. And of course, there are a lot of people that comment in my tutorials and tell me that there's another way to do this. And of course, it's true that I'm like the teacher here trying to teach something, but I always learn from you guys. So if you think that I'm doing something stupid here, or there's an easy way to do this, please let me know in the comments below. And you're not just letting me know, you're letting everybody else know how to do that in a much more easier way. So let's dive into some of these things. So the first thing that you see here is the semivariance function. Let's skip this one because we want to go through this the same way we've did it here, so you guys understand why we're doing these kind of things. Okay, so sorry for that. So you can see that we have the different points in here, and the first thing that we said, we need to create what we call the distance matrix. So it's going to be the distance between point 1 and itself, the point 1 and the point 2, the point 1 and point 3, and so on, and we're creating this distance matrix. So how do we do that? We're going to create a function. So by the way, we have two distance matrices, so I've separated these. You'll see later on why. So this is going to be the distance matrix to the known points, and this is going to be the distance matrix for the unknown point that we want to estimate. Okay, so let's go to the distance matrix of the known points. So this function is going to take x and y as values. These are the x and y for the known, for the known points. And now I define a temporary list here. I just call it temp list, and it's an empty list. And then I create a for loop that is going to loop through the x and y values. So if we have the x and y, so we have a list of all the different x's and a list of all the different y values. So I loop at both of them at the same time. So we'll have, so in the first iteration, I'm going to have access to the first value in this list and the first value in this y list, which is the x and y for the first point. I do that by using the zip in here that allow me to loop through multiple lists at the same time. So I will have access to the first value, or to the values, to the elements of x by the e here, temporary variable or value here, and I access the elements in y by g. Okay, since we want to do all possible combinations, we need a nested for loop again. So we are going to iterate through the same values of x and y again, but now instead we are going to assign them to E and D. So for each one of the values in x and y, we're going to loop through all the values. So we're going to have, for example, this is the first element. We're going to have the first element here, then go to the second, the third, and so on. When you go to the last one, we go back here and say we go to the next one, and then we loop through all the different things. So basically what we're doing is we're fixing the point 1, and then we iterate all over these points. Okay, when we reach the last one, which is the second for loop, we go back again, we fix the point P2, and then we iterate through all the different values. Okay, then what we do is we calculate the distance between that first value here, which is accessed by the x is accessed by the x, and the y is by the g, and then we calculate the distance between that and the point that we're iterating over in the second for loop. We calculate the distance, and what we do is we append that distance to this temporary list. So when the for loop ends, we're going to have all the different distances, in this list. But that's a problem. Now we have a list, but what we need is a matrix, okay? So we need one way to make all of these so it's going to be a list inside a list. So what we need to do is we need to have this one as a list by itself, this one by a list by itself, and so on, and all of them inside one big list. So that's basically, if we convert that to an NumPy array, we're going to have a matrix, okay? And this is exactly what we're doing here. We're creating a variable called distance matrix, and just forget about this part for the moment. And inside this list, we're doing the list manipulation. So inside of it, we're creating a for loop that's going to iterate through the values inside this list and divide them into smaller lists with the length of x. Okay, so for example, if we have 5 points, so every 5 points we're going to create a list and move to the next one. If we have 10, this is going to have 10 values and move to the next one. And that way we have now all of these rows, each one of them in one list by itself, and all of them inside one big list, which is later on converted to a NumPy array, which means a matrix, using the NumPy array here method. Okay, then so basically this is what this one does. It's going to give us the distance matrix, and you can see that it returns this one. So we give it the x and y, and it gives us the distance matrix. That's great. Now the second part, which is in a function by itself, which is this one, we're going to calculate the distance matrix of the unknown point with all the different points that we have, and this is very easy to. We do the same exact thing in here, but instead of having just x and y, so we have the x1, x2, y2, x2, and y2. These are the known points and the unknown point. The known points are the x2 and y2. We are going to iterate over all of these, and again calculate the distance between these different points and the unknown point, which is x1 and y1. And then the distance that we're going to get, we're going to append that to a list. And since it is just one column here, we are going to assign that directly to a NumPy array. So we need that list to be converted into a NumPy array. Okay, and this is going to return that NumPy array here. Now we've covered this part where we calculate the distance matrix. Now the next thing is to use that assumption of the spherical variogram and define this function here that takes one of these distances and give us the semivariance at that of that distance, and then we are going to have this one here. Okay, so that's what we're going to do with this semivariance function. It takes the nugget, the cell, the range, and that distance. Okay, so then what we can do is we apply this one to all of the different values in that distance matrix that we've created. Okay, so it's basically this line of code here is the exact same equation that we have in here. So C1 plus C and so on. Okay, so we've defined these values, but we can change them later on if we want so, or we can just directly insert the values in here, the nugget, the cell, and the range, and the distance, and we're gonna get the semivariance of that one based on this model here, of course. And ultimately, if you want to make this a little bit more complex, you can define inside this semivariance. You can maybe add another thing here, which is maybe the model type. You can give it and tell it, for example, whether in the model, if it's spherical, do an if condition here. If this value, if the type, for example, is equal to spherical, use all of these. If it's exponential, use these, and so on. And that's how you make a complete one that uses any model that you have. But in our case, we're gonna make this basic, and it's gonna use just this variogram, which is a spherical one. Okay, so we've calculated semivariance for any values of h that we have. We're gonna be able to calculate the semivariance of that one. Okay, now I could have done this same thing for I've separated two different things, like here, to calculate the matrix for the known point and for the unknown point in two different functions. But in here I wanted the same semivariance to calculate the same function, to calculate either this one or this one. So that's why I've added these if and else conditions. So and of course the next step is calculating this, and also at the same time adding these ones. Okay, so we said that these basically to make the matrix, take account in that thing that we said that the sum of the weights is going to be equal to 1. So we need to add a bunch of ones in here so that we get the 1 when we do the multiplication or the dot product or whatever, the things that we're going to do later on. Okay, so to do that, so what I've done is I created a variable. Yeah, by the way, this is if the shape of the SV is, the number of columns is more than 1, which means we're talking about this one, because usually since this one is estimating just 1 point at a time, so this is going to be always having just one column. So if it's more than one column, then we're talking about these, not this one. Okay, so if the shape is, so this is the index 0, so basically the shape, it's going to return a tuple of the the shape of the matrix, the column and the rows. So if the number of columns is more than 1, then we're talking about this part, and we need to apply all of these things. Okay, so I'm creating a variable that's called one's call. So I'm creating a column of 1. That's really basic. Basically what I'm doing is I'm creating a column of 1 with the same shape of the rows of the SV here. So if I have, for example, 4 rows, I'm going to have 4 ones in here, and so on. Then what I'm going to do in the second line here is I'm inserting that column in the end of the SV in here. So what I've done now with that column, which was alone, and now I've inserted that in this distance, this semivariance matrix that I've created. And now what I need to do is I'm going to create another thing here, which is a one's row, which is this one. And then what I've done the same again is I've inserted that in the bottom with this line of code in here. So I've inserted that in the bottom here. Now the problem is I'm going to have 1 here. So because I didn't define a 0, but I need to change this to 0. And this is what this line of code is. I'm telling the script to go to the last element in the corner in here and assign a 0 value to that one. Okay, now in the case where the shape is equal to 1 or less, it cannot be less than 1, but in the case it is equal to 1, I'm going to assign, creating just one here, again with the shape of the SP, which is this shape, of course. And I'm inserting, that one in the end. It's going to give me this one here. So, and then later on, what I do is I transpose that one. So it's going to be like this one, okay? So transposing a matrix. So instead it's going to be, instead of horizontal matrix, it's going to be a vertical one, okay? So, and whatever is the matrix I'm going to have, whether it is this one or this one, it's going to return that matrix in here. So this is what the semi-variance is going to return. It's going to return either this one or this one based on the input. Okay, so we've covered this one, we've covered this function here, we covered this function, and now we need to cover the ordinary Kriging function, which takes the x, y, these are the points, the x and y coordinates of the points that we have, and takes the x and y of the unknown point that we want to estimate and the variable that we want to estimate. Okay, now here what we do is, since I've imported that variable and it's going to have this is basically, it's going to reshape that variable to have a column and a row value, because when you import that and use like this one, where is that? Okay, let me go back here. So this one is going to have a shape of, let's say if it's just 5, 5 values, going to be 5 comma and there will be nothing, which you cannot use later on. So what I do is I'm reshaping that to have the shape of the shape of the variable and then 1, so 1 column. Okay, then what I do is I transpose that so that I will be able to use it for the dot product later on here. I transpose that matrix using this variable here. And then you can see that we have the matrix distance for the known value. I call that n in there. It takes the data x and data y. These are the known values. These are the data x and data y. These are the known values. And then we calculate the distance matrix for the unknown values, and I'm here. I'm calculating distances in here. And I'm calculating that for the unknown values. So I'm using that distance to u again. I give it the unknown x, unknown y, and the data x and data y, which are these ones. And then what I do here is the known semivariance. I'm calculating the known semivariance, which is this one. So what I do is I just use that semivariance function. It takes the nugget, the cell, the range, which are defined already here. And what it does, and then it takes the matrix, the known matrix, and it's going to give me the a matrix of the semivariances of that one, of the known values, and then do the same thing again for the unknown values, which is going to use that if condition here, because it's going to have just one column and give me that unknown semivariances there. And now what I need to do is to go to the next step, which is basically doing the inverse of that semivariance matrix. So what I'm doing here is the inverse of the known semivariance. I use the numpy line, this function here, to get the inverse of the known semivariances. So I already have this part here. And the next step is to calculate the weights. And you can see to calculate the weights is basically to multiply this one by the semivariance of the unknown semivariance. So we're multiplying the inverse of the known semivariances by the unknown semivariances. So that's the one that I've calculated in here, multiplying this one by this one to get the weights. And then as you notice, we have an additional value which is going to be in the last one. So instead of 5 points, I'm going to have 6. What I'm saying here is I want to delete the last one here, the weight, so that we have so that we can do the dot product. And then the estimation now is going to be the dot product of the, which is this one. It's going to be the dot product of the variables. Okay, the variables that we have. which are the variables that we want to estimate, and the weights. And what this is going to return is going to return of the value that we want to estimate at that specific location. Now what I've done here, this is something that you can do later on, is if you want to create if you wanna so basically this, we can stop right here, and this is the ordinary Kriging function that's going to estimate the value out of an unknown point based on some known points. So it's going to return the estimation. But let's say that you have a bunch of points and you want to estimate all of these points based on some known points. Then we can go a little bit to some advanced stuff here. We are going to create a mesh grid. So basically we're taking line space here, x mesh. It takes the minimum x, the maximum y, and we define a resolution here. So this is going to be how many points are to be interpolated between the x and mean x and y. So then we define the resolution here. So for example, if you have the minimum value is 0 and the maximum value is 10, if you set the resolution to 10, it's going to be value is going to be 0, 1, 2, 3, 4, and so on. If you define this to 20, it's going to be maybe 0.51, 1.5, and so on. So this is going to control the resolution of that grid. Okay, then we use that mesh grid and create an X mesh, Y mesh, and so on. And I don't really want to confuse you guys here, so basically then later on we're going to iterate through all of these X's and all of these different Y's, and we're creating a grid with X and Y, so with all the different combinations of X and Y. And then what we do is we use these X and Y's and we use the estimated. This is a value of estimated. Then we take that X and Y and we use that ordinary Kriging, of course, to estimate the unknown points in that grid, and we get the estimated value as a z value here. We append that to the EZ, so we're gonna have X and Y and the estimated z value, and we are going to add that to a data frame. So we're gonna have X and Y and Z. So, and later on we can if I run this script now, so basically this is going to be the data set. We've imported that pd read that data set. This is the data set that we have, and then we use this method here. We take the x column and turn that into an imply array. We take the y column and turn that into an imply array, and also this one, so that we will be able to use these as matrices and manipulate them using the function. And later on we use this interpolation function here that takes the x and y and the variable, and it's going to do all of the different things. So we're going to insert these in the OK, which is the ordinary Kriging function here that takes all of these that we covered, and it's going to do the interpolation and give us all of the different values that you see in here. For x and y we have this z value and so on. What you can do later on, you can either export this to a CSV file and use it in your favorite software to make a map, or you can use libraries like Matplotlib or Plotly, or maybe you can view these in 3D and you can do all kind of cool stuff with this Kriging. So that's it about. So the main purpose of this video was to show you that this is possible. That's the first thing that I wanted to cover. The second thing is to give you an idea how things work in Python, and without actually really diving too much into the details, like because if I want to go into details, I need to cover what is NumPy and all the different things, and what is pandas, and then I need to go and cover Matplotlib by itself, and I need to cover all of these functions and so on. So this is mainly for people who are used to Python or beginners in Python. So you can go and copy this one. You can follow the video and try to do this yourself and play around. You can do debugging by printing the, for example, you can print the transposed one here and see the difference between that one and the initial one, and try to follow, of course, these slides that I've shown you in here, so that you know what are you doing and why are you doing that. So I hope this video was informative for some people. I might missed few things or did few things in the wrong way, or there's an optimal way to do that. I'm looking forward to know that, guys. Let me know in the comments below what do you think about this one, whether I should do more things like this, like a variogram modeling, and maybe combine that with this one so we'll be able to do estimation in here. Maybe you want to see some visualization in the next video. Please let me know in the comments below. Share this video with anyone who might be interested. And with that being said, I think that's it for this tutorial, and see you in the next one.